So carbon spectra are much easier to analyze than proton spectra because the signals aren't split. Now, the lack of splitting in a carbon spectrum is a consequence of the low natural abundance of carbon-13. So splitting occurs when those two NMR active nuclei, like the two protons that we've talked a lot about, are close to each other. Because of the low natural abundance of carbon-13 nuclei, the chance of two carbon-13 nuclei being bonded to each other is very, very small. And so that means there's no carbon-carbon splitting that's observed. Because remember, most of carbon is carbon-12. Now, a carbon-13 can be split by nearby protons. That's usually eliminated from the spectrum by using an instrumental technique that decouples the proton-carbon interactions so that every peak in a carbon-13 NMR spectra appears as a singlet like you see here. Now, when we look at this, many things are the same, which makes it nice. The chemical shift, right, we read from here to here. I want you to notice that the x-axis is different, right? We go from 0 to 200, where in the proton we went from 0 to approximately 10, okay? I also want you to notice there's a lot more noise that's associated with these types of spectra because there is that low abundance of carbon-13. So this is an example of a spectra where we have two peaks, right? Because there's a carbon here and a carbon here. And so one of the things that's also really nice is that the shielding that we learned about is echoed in carbon-13 spectra. So for example, the carbonyl, right, is much farther downfield than the CH3. So we can draw some parallels, which makes it very nice to analyze. Now, so as I've already mentioned, our two big features, or the big things that we are going to get at a carbon-13 spectra, are the number of signals and the chemical shifts of those signals. The number of carbon signals gives us the number of different types of carbon atoms in a molecule. So, for example, we've got dimethyl ether. There would be one signal here because both of those carbons are equivalent. In chloroethane, there would be two signals. In methyl acetate, there would be three signals. Now, because these carbon-13 signals are not split, the number of signals, right, just equals the number of lines in the carbon-13 spectra. So the number of signals equals the number of lines because the signals are not split. Right? So unfortunately, though, peak intensity is not proportional to the number of absorbing carbons. And so what that means is carbon-13 is not integrated. So here are common chemical shifts that we find in carbon-13 spectra. You can see the chemical shift for a carbon, for a hydrocarbon, is between 5 and 45. Once you put an electronegative atom on there, like a nitrogen, oxygen, or halogen, we shift down to 30 to 80. The carbons in a triple bond are 65 to 100. A double bond are going to be 100 to 140. Benzene carbons generally show up 120 to 150. And then carbonyl carbons are in the range of 160 to 210. So these are very helpful, but again, they're going to kind of mimic that pattern that you learned in the proton NMR, where carbons bonded to more electronegative atoms are going to be farther downfield. Now, let's look at a few carbon-13 NMRs, some examples here. We have one propanol, which is shown here. The carbon that is closest to the oxygen here is going to be the farthest downfield. That's going to be this carbon C. Then you would expect carbon B to be next, and then carbon A as well. So this tells us 3 types of the carbons that we have, and it also indicates that this carbon is attached to an oxygen. Again, just another quick example. Here's methyl acetate. We have a carbon here, a carbon with a carbonyl, and then this carbon is bonded to an oxygen. The carbon of the carbonyl is going to be farther downfield. We're going to see it here, the CB, because this particular carbon of the carbonyl is also bonded to this oxygen. So this carbon is bonded to 2 oxygens, so it's farther downfield. This carbon is bonded to 1 oxygen, so it's going to be here. And then this carbon is bonded to no oxygens and just the carbonyl, so it's going to be here at A. So again, that's all we've got to say for carbon NMR spectroscopy. Much, in my opinion, much easier than proton spectroscopy. So this ends our 3rd chapter of spectroscopy, Spectroscopy C, and it also ends our discussion of spectroscopy. We'll work some examples in class, and as always, please come and see me if you have questions.